Good day. My next topic is the current status of cardiac cell repair therapy, hope or hype. And maybe I say hope or hype or both. And I think it is a mixture of both, another very complex area. Now, the goals of cell therapy and acute myocardial infarction of stem cell therapy are really based upon this diagram from Dr. Mark Pfeffer that shows that with acute myocardial infarction involving the apex here, this goes on to cause infarct expansion, followed by altered stress-strain relationships, leading to chronic LV dilatation, remodeling, and chronic heart failure. And the idea was really to try and see if we could interrupt this process, whether it be by drugs and also perhaps by stem cell therapy. What happens with adverse remodeling is that you get reduced revascularization in this area and increased apoptosis. And the idea with stem cells is that they could prevent that either by regeneration or by the elaboration of paracrine factors, which may in turn interrupt this vicious cycle of reduced vascularization, apoptosis, LV remodeling, and heart failure. Now, early studies basically showed that it was safe and feasible. Studies predominantly using bone marrow stem cells. Skeletal myoblasts were used in the early days, about 10, 12 years ago, but they resulted in ventricular arrhythmias and ultimately fell into dysphagia. The results, at best, modest. An improvement in LV function of about 3%. In some studies, there was an improvement in perfusion, remodeling, and in one study, coronary flow reserve after myocardial infarction. The clinical outcomes, I should emphasize, none of these studies were powered for hard clinical endpoints, but interestingly enough, the trends were always favorable in the right direction. The downside is this: when you looked 1 week later, the majority of these implanted stem cells had disappeared. And there was no evidence of myocyte regeneration using existing therapy. So why the trend towards a benefit if there was no evidence for regeneration? And this is really what gave rise to the so-called paracrine hypothesis as an explanation for beneficial effects. In other words, it's not that the cells are regenerating new myocytes, but that they are releasing and secreting paracrine factors, which are in themselves beneficial. And then there's the question of whether endogenous cardiac progenitors could be stimulated. Recent trials over the last 5 years, the results have been mixed. And unfortunately, there have been concerns justifiably raised about scientific misconduct. I'll come back to that. New questions have been generated. Probably we have to say that a lot of the indecision and difference in results reflects an incomplete understanding of the basic mechanisms of benefit. We've still got a great deal to learn. And there are many new cells and approaches currently undergoing testing and evaluation, which I will illustrate in the next few slides. If, I might add, if we develop cells or properties or approaches that do result in myocardial regeneration, we'll have to go back and revisit the whole safety aspect, because cells that can regenerate myocytes, but they can also regenerate tumor cells. And so that safety issue will still have to be readdressed as new and different approaches come to fruition. The one area that's really, I think that has been disappointing is the area of refractory angina. And the reason I say it's been disappointing is I've always felt that this is the lowest hanging fruit. And these are patients who have refractory angina. They are not amenable to reperfusion, PCI, revascularization. Their quality of life is extremely limited. And there have been 3 trials, double-blind studies of autologous CD34 cells for the treatment of refractory angina, the largest being the RENEW trial I was on the Data Safety Monitoring Board of this trial, and it was terminated by the sponsors due to lack of interest after 303 patients had been enrolled. If you look at the three trials, this is month 3, month 6, month 12. Yellow is placebo, CD34 cells in orange, and you can see a significant increase in post-exercise time at all 3 time periods. Pretty encouraging. And this trial was also going very much in the same direction before it was stopped. There was actually a reduction in mortality in these trials, although the trial was not powered. None of them were powered for that endpoint, but the trend was very favorable. And I'm disappointed that these trials were not continued, because I think they may well have had a positive result. More recently, my colleague Amir Lerman at the Mayo Clinic, working with Dr. Tim Henry, has just published a paper in, I think it's, which interventional journal is it? I think it's either JACC or Circ Intervention. 20 patients with microvascular dysfunction, effort angina 3 or more times a week, no obstructive coronary disease based on a 40% stenosis. And this is after a single intracoronary LAD infusion of isolated CD34 cells. And this is the measurement of coronary flow reserve. Now, in 2 or 3 patients, coronary flow reserve decreased, but in the majority, coronary flow reserve substantially increased. And let me just get this out of the way here, with a mean change of 0.62 on this axis of coronary flow reserve. So pretty impressive in patients with microvascular dysfunction. And then the second half of this study looked at the frequency of angina. To get into the trial, you had to have 3 or more episodes a week. And overall, there was a significant reduction, highly significant, in frequency of angina. And the mean change was at least 2.34 episodes per day. So again, I think along the lines of patients with refractory angina, who I think may be amenable to the angiogenic effects of stem cells, I think the same thing actually applies to patients with microvascular dysfunction. So where are we at the moment? Do we have grounds for optimism? Yeah, ongoing basic research on multiple fronts and in many countries is very active, but somehow the message has been lost in clinical translation. Clinical trial results have shown safety, modest benefits, and modest trends in the right direction. The paracrine hypothesis is a plausible biologically and a potential therapeutic target. But the concerns are that the benefits have only been modest. There are many neutral trials, and depends on whether you think the glass is half full or half empty. But I believe that expectations, both from physicians, the public, and the media, I believe that these have been unrealistic. And then when you have unrealistic expectations and the trials come out and they're mainly neutral or the benefits are very small, there is an overreaction in the other direction. There are valid perceptions in the scientific community over the extent of stem cell research funding, and a feeling that this whole field has been overfunded and that money could have been spent more wisely in other directions. It's open to discussion, but the perception is certainly there. And then, unfortunately, there have been a number of reports reports that have highlighted the negative impact of scientific misconduct and scientific fraud. And that has hurt the entire field, and we're still recovering from that. I think we can pose 2 questions generated by recent events. The validity of the basic biologic constructs underpinning almost 2 decades of trials is under scrutiny. Putting in bone marrow cells and expecting them to generate myocytes is probably unrealistic. And does the future of cardiac cell repair therapy require a fundamental change of direction? And if so, how? I think that some of the biological constructs are still valid and require further testing, such as bone marrow stem cells in patients with refractory angina and in patients with microvascular dysfunction. But in other areas, in terms of regeneration of myocytes, I think we have to look in different directions. So a good question to ask, why proceed clinically when we don't really have the basic questions, or we don't understand some of the basic biology? Well, trials provide some answers to preconceived hypotheses, but trials also generate new questions. And let's go back in history a little bit. We've been using aspirin for 120 years before we knew how it worked. Statins are lipid-lowering drugs, but we now understand much more about the pleomorphic actions of the statins. ACE inhibitors were developed, and I'll talk about this in my next talk. ACE inhibitors were developed as antihypertensive agents, but we know that they have fundamental effects on the biology of atherosclerosis. We only knew that because of the trials. We didn't know that before. In fact, the knowledge that ACE inhibitors affected ischemic events and reduced ischemic events came out as a byproduct of a heart failure trial. What about aldosterone antagonists, a 30, 40-year-old diuretic that no one really used until Dr. Pitt came up with his series of trials showing that the aldosterone antagonists were pivotal drugs in the management of heart failure. And preclinical studies will not answer complex questions about the timing and the methods of cell delivery. So I think we should continue understanding that there are limitations to what we know. Look at the story of sacubitril valsartan. 2015, the paper was published. But I refer you to this brilliant paper by Dr. Eugene Braunwald, who pointed out that it took 50 years from the isolation of the angiotensin converting enzyme to the development of sacubitril valsartan. 50 years. And we think we were going to solve the issue with stem cells in 5 or 10 years. We were naive. So there are ongoing studies. This is one from Dr. Joe Wu at Stanford. And this is the first trial, human pilot study of embryonic stem cell derived cardiac myocytes that may have the potential to regenerate myocardium. It has just started, but an encouraging development. And in this review by Drs. Povzik and myself, we summarize 3 or 4 future approaches. The first is, as I mentioned, the trials of cell therapy for patients with refractory angina have all pointed in a very positive direction. And I hope these trials will continue in addition to further trials of microvascular dysfunction. Cardiomyocyte regeneration with induced pluripotential stem cells and ESC-derived cardiac myocytes, embryonic stem cells. This is another approach that really is directed at restoring and renewing myocardium and replacing myocardium. And then there's the whole issue of biological patches, bioengineered structures which have been seeded with cardiac myocyte stem cells in the hope that they will engraft. And I think these are 3 major new directions. And one of the first studies with this technique has been published, a small trial, 24 patients, non-ischemic dilated cardiomyopathy from Japan, of using autologous stem cell patch implantation for patients with heart failure and non-ischemic dilated cardiomyopathy. Responders, as defined by no MACE and no heart failure event, occurred in the majority, but at about 60% responded, 40% didn't. And in those who responded without any of these events, there was a clear improvement in left ventricular function and functional capacity. But it's not that simple. What we need is for the various cell types of the heart to communicate and coordinate. This is vital for cardiac homeostasis. And the key is for regenerated cardiac myocytes to integrate with other cardiac tissues like gap junctions, extracellular matrix, blood vessels, and lymphatics. So it's a very complex series of procedures and networks that need to be established. This is a fascinating matrix metalloprotein called agrin, which promotes coordinated therapeutic processes leading to improved cardiac repair in pigs. This paper, published in Circulation, porcine model of ischemia reperfusion injury, used recombinant human agrin. And what you see in the porcine model of myocardial infarction, orange is dose 1, green is 2 doses of the drug, huge improvement in ejection fraction, huge reduction in left ventricular end diastolic pressure. And if you look at at 28 days, anything in black is scar, anything in red is healthy. And this is what we saw with 1 dose, and this is what we saw with 2 doses, almost complete regeneration and resolution of scar. I'm on the advisory board of this group. We are hoping within the next year to start a human clinical trial. But a single dose is capable of reducing ischemia reperfusion injury and improving heart function, demonstrating that agrin could serve as a therapy in patients with acute myocardial infarction and heart failure. So I think we can make a strong case for translational research. The clinical need is unmet. The potential is huge. Adult stem cells are plastic and can change their characteristics. It's intuitively appealing, but the history has been relatively short but unfortunate. We need to acknowledge the past mistakes and focus on new approaches. And I believe that abandonment of the entire field would be premature at this time. But I think we also need to understand that some of the criticisms are very justified. And rather than resenting them, we need to acknowledge past mistakes and focus on new approaches. Thank you for your attention.